Yeah, hello everyone. Welcome back to Solid State series. This is Solid State part 15. And in this video, I'm going to talk about the structure of NaCl, the structure of rock salt. So in this, what is the position of Na plus ion, position of Cl minus ion, coordination number of cation, coordination number of anion, packing efficiency, all these parameters, all these points I'm going to discuss in this video. And instead of getting into NaCl structure directly, so first let us take the exact meaning of radius ratio, exact meaning of coordination number. After that, we'll start our discussion, that is structure of a NaCl. So in case of ionic solids, it is necessary to know about a radius ratio. What is the exact meaning of a radius ratio? Based on radius ratio, how to know the structure of the given ionic solid? That is our discussion. So in ionic solids, cation is smaller, anion is bigger. But that is in general. There may be some deviations also. But in most of the cases, cation is smaller in size when compared to anion. So radius ratio, it is the ratio of radii of smaller ion to bigger ion. It is the ratio of radius of a smaller ion to radius of bigger ion. So in general, cation is smaller in size. Hence, we can simply write a radius of cation by radius of anion. And obviously, it is a ratio and it has no units. It has no units. And most importantly, this radius ratio will help us in two different areas. One is finding the coordination number and also in the determination of structure of that particular ionic solid. So here, most importantly, two important considerations here I have to discuss. In ionic solids, anions and cations are assumed to be hard spheres. Of course, that is the known point. They are assumed to be hard spheres and always they are touching each other. Cation is in contact with anion and vice versa. Anion is in contact with the cation. And anions are in contact generally, but may be close enough to be contact with one another in a limiting situation. Anions are not in contact generally, because if you take two anions, there may be some repulsive interactions. So in general, they may not be in contact, but they may be close enough to be in contact with one another in a limiting situation. So what is this limiting situation? In the examples we'll discuss. And particularly cation, due to its small size, generally it occupies voids, maybe tetrahedral voids or octahedral voids. So the cations which are occupying voids, always they try to be in contact with the, what do we call a anion. In order to be in contact with the anion, the cation should have some minimum radius. Some minimum radius. See, for example, this is one anion, this is another anion, and between these two anions, there is a void, and whenever cation is occupying that particular void, in order to be in contact with these anions, so the cation should have some minimum radius. If the radius of that cation is less than minimum, definitely that solid is incorrect. It does not occupy, cation does not occupy that particular void. So based on radius ratio, we can identify which void is going to be occupied. Based on that, we can also identify coordination number. And with the help of these things, we can define the basic structure of that ionic solid. For example, if limiting radius or radius ratio is from 0.155 to 0.225, So here 0.155 and maximum should be less than 0.225. So in between, so here 0.155 starting from this. So here less than 0.225. It will definitely occupy which void, that is a triangular void. In that situation, coordination number is 3. But already I told you, so these planar voids, in reality, they do not exist. They do not exist means all solids are a 3-dimensional. And if radius ratio or limiting radius is 0.225 and less than 0.414, in that situation, that cation will occupy tetrahedral void. Tetrahedral void means the coordination number is 4. For the sake of explanation, what I am trying to convey, there is an ionic solid. In that, radius of anion is, let us take 1 angstrom, and anion is forming the lattice. Radius of anion is 1 angstrom. And if radius of cation is from 0.225 to, that is 0.414, but 0.414 is not included in this range. 0.225 to, for example, that is 0.414 angstroms, but this is not included. In that situation, that a cation will occupy tetrahedral void. That means minimum it should have 0.225. If radius of anion is 1 angstrom, radius of cation should be minimum 0.225 in order to occupy that void. If it is less than 0.225, definitely it won't occupy what do we call tetrahedral void. If it is great 0.414 or greater than 0.414, in that situation also it cannot occupy tetrahedral void. Only in this range it will occupy tetrahedral void, and the coordination number is 4. And what is the example? Zinc sulfide structure. And 0.414 to 0.732, very clear here, 0.732 is not included. In that situation, cation will occupy octahedral void. Coordination number is 6. The best example is NaCl. And finally, 0.732 to less than 1. In that situation, it will occupy cubic void. And here, the coordination number is 8. And here, the best example for this is cesium chloride. So we need to discuss 6 to 7 different examples. But in this video, I am going to discuss the first one, that is rock salt type structure, NaCl type structure. But the most important thing the student has to know, one should know, just location of cation and anion, where cations and anions are present in this. That will be 100% sufficient. Remaining things can be developed spontaneously. If you have complete clarity on internal structure of cubic solids, cubic unit cells, 100% by just remembering 2 points. What is the location of anion? What is the location of cation? Each and every parameter can be derived or evaluated spontaneously. But let us take first NaCl type of structure. What is the statement you need to remember? So here, just position of anions. Anions are forming FCC lattice. You know, FCC lattice means a face-centered cubic. So anions are present at 2 places. What are the 2 places? One is face center, another one is corner. Anion is forming FCC lattice, CCP or FCC lattice. And cations occupy all octahedral voids. Cations occupy all octahedral voids. If you can recollect, in CCP or FCC, octahedral voids are present at a body center and edge center. Body center and edge center are octahedral voids in FCC lattice. The most important thing, NaCl or NaCl type, any structure if you find, if you come across, anion is forming FCC lattice. That means anions are occupying all face centers and corners. And the cations, it will occupy what do we call a body center and all edge centers. This is the only information the student or anybody should know, only information position of cation and anion. And here Cl minus ions are present at face centers and corners. Remaining things you see I will develop spontaneously. And Na plus ions are present at a body center and edge center. And if you take 1 unit cell of sodium chloride, 1 unit cell of sodium chloride, not effectively, totally. So face centers are 6, corners are 8, therefore 14 chloride ions. Body center is 1, edge centers are 12, therefore 13 Na plus ions. So this is a total number, not effective number. So totally that is 14 plus 13, 27 ions are present in 1 unit cell of NaCl, FCC unit cell. So this is FCC, but ionic structure it is. So anion is forming FCC and cations are in the voids. But if you want to find the effective number of chloride ions are present at face center. The contribution, when the particle is present at face center, its contribution is 1 by 2. Not only at face centers, anions are also present at corners. Corners are 8 and the contribution of corner is 1 by 8. So 6 into 1 by 2 plus 8 into 1 by 8, effectively there are 4 ions, 4 anions. Similarly, effective number of Na plus ions. Na plus ions are present at body center. Body center is 1, contribution is 1. Body edge centers are 12. Contribution of edge center is 1 by 4. So this is 3 plus 1. So effectively there are 4. You see the positions, if you know, you can calculate all these things spontaneously. And if you take the mass of 1 unit cell, so 1 unit cell has, first let us take 8 ions effectively. 8 ions are nothing but 4 ionic pairs, 4 Na plus ions and 4 Cl minus ions, because here we have calculated. And if you take the mass of each unit cell of NaCl, if you take 1 unit cell of sodium chloride, what is its mass? That unit cell has how many ionic pairs? 4. What is the formula mass of sodium chloride? Sodium is 23, chlorine is 35.5. Chlorine or chloride, the mass is same. Sodium or Na plus the mass is same. 23 plus 35.5, 58.5. So the formula mass of sodium chloride is 58.5. So 4 such formula units are present. So that is 4 into 58.5, that is 234 AMU. This is each unit cell I'm saying, each unit cell I'm saying. But if you take mass of 1 mole of unit cells, 1 mole of unit cells in grams, 1 mole of unit cells in grams means the first mass of each unit cell is 234. 1 mole of unit cells means you have to take Avogadro number of unit cells, so that is 6.023 into 10 power 23. 1 mole of unit cells, but I am reporting my answer in grams. But here it is, you are getting your answer in AMU, and 1 AMU is equal to 1.66 into 10 power minus 24. 1.66 into 10 power minus 24, that is in grams. So here 6.023, 6.023, 1.66, if you multiply, you will be getting 10. 10 into 10 power 23, 10 power 24, 10 power 24 into 10 power minus 24, that is 1. So 234 grams. So here, this is mass of single unit cell and this is the mass of Avogadro number of unit cells, but it is expressed in grams. I converted that AMU mass into grams. And similarly, if you find the number of unit cells present in 1 mole of sodium chloride solid, 1 mole of sodium chloride solid means 1 mole of sodium chloride solid, not 1 mole of unit cells. 1 mole of sodium chloride solid means 58.5 grams of NaCl. 58.5 grams of NaCl. Here we have calculated 1 mole of unit cells of 1 mole of unit cells of NaCl mass is 234 grams. So here 234 grams of NaCl, 234 grams of NaCl contain 1 mole of unit cells. Then 58.5 grams of NaCl, obviously that is 1/4 of that, because 58.5 is 1/4 of 234. 234 grams of NaCl contain Avogadro number or 1 mole of unit cells. 58.5 grams will contain how many? And the most important thing is the coordination number of Na plus and coordination number of Cl minus, and how this coordination number, with the help of diagram, I'll discuss. And if you take edge length of this NaCl unit cell, edge length of this NaCl unit cell, so this is corner particle, so this is corner, and this is body center. Sorry, edge center, sorry, not body center, edge center. So this is corner, and this is edge center. Already told you, in all these ionic solids, Na plus ion, not only Na plus ion, cations always try to be in contact with the anion. So for all ideal calculations, in reality, how it is present, we don't know. But in the calculation part, paper and pencil work, when you are doing, we are assuming that Cl minus is in contact with Na plus, like this, Na plus is in contact with Cl minus. So this total distance is called, what do we call, edge length. So this is this part is radius of anion, this is diameter of cation, this is radius of anion, and in case of NaCl type of unit cell, edge length is 2 times of sum of the radius of cation and anion. And also one more point, for all ideal calculations, of course, the range is, when it is occupying octahedral void, the range is 0.414 to 0.732, but 0.732 is not included. But for all ideal calculations, we take radius of cation is 0.414 times of radius of anion in the calculation part. Because in reality, cation radius may not be exactly 0.414 times of radius of anion. It may be slightly more than that, it may have. But in the calculation part, all for ideal calculations, we take radius of cation is 0.414 times of radius of anion. And if you see the arrangement of particles in one phase of NaCl unit cell, you see this is one phase. So this is corner, and this is a phase center. And this is edge center. These are all edge centers. And this one we have just calculated. This is what we call edge length. This is edge length. And one more thing, this is called what we call this distance. If you can recollect, this is the phase diagonal. So that phase diagonal is equal to root 2a. Phase diagonal is equal to root 2a. And the most important point here, always students get confused in these calculations. In reality, between this chloride ion and this chloride ion, there may be some gap. They may not be in contact, because this is negative charged particle, this is negative charged particle. Sometimes Na plus ion radius is what do we call 0.414, greater than 0.414 times of radius of anion. In that situation, to accommodate that Na plus ion in the octahedral void, what happened is anions will move in opposite direction, because cation is having more than expected size, because 0.414 is ideal. If it is 0.414, I mean, I'm talking about cation radius. So 0.414 times of radius of anion. In that situation, there is no distortion. That crystal is ideal. But if by any chance, if the cation which is coming into the void, if its radius is greater than 0.414 times of radius of anion, to accommodate that cation, anions will move slightly in opposite direction, then the crystal is slightly distorted. But in reality, I told you, in reality, there may be some gap, but for ideal calculations, we are taking 0.414 times of radius of anion. In that situation, so this anion will be in contact with this, and in all the calculations, we also take a root 2a is equal to 4 times of radius of chloride ion in this NaCl, because chloride ion is forming FCC. Chloride ion is forming FCC. So for all ideal calculations, we take cation, there is no distortion at all, and cation size is exactly 0.414 times of radius of anion, and comfortably it sits in the octahedral void. There is no distortion. In that situation, what do we call phase diagonal root 2a is 4 times of radius of chloride ion. And here this is the arrangement. But the most important thing is we need to talk about the coordination number of cation and coordination number of anion. Coordination number of, first let us take coordination number of anion. Anion is present at two places. Coordination number of anion means the number of nearest Na plus ions. The number of nearest Na plus ions. For example, you have to imagine, and here I will try to show the coordination number of, what do we call, this is anion, and this is located at the phase center. I'll also take a cation. First, let us take this one. Chloride ion, which is sitting at phase center. Now you can see this is edge center, edge center, edge center, edge center. But most importantly, this is also in contact with the, you can see exactly backside there is body center. If you see this edge center to body, edge center to phase center, the distance is a by 2. A by 2. Of course, this is also at a by 2. All the four are at a by 2. But backside to this, at a by 2 distance, there is one particle sitting at body center, that is Na plus ion. At what distance? A by 2. And above this, top of this, there is one more unit cell. That is one unit cell. Top of it, there is one more unit cell. In that unit cell also, there is body center particle. And this phase is common for both the unit cells. And here, this Cl minus ion is in contact with the body center of this unit cell, body center of adjacent unit cell. At what distance? A by 2. At what distance? A by 2. So obviously the coordination number of Cl minus ion is 6. So what are the, for phase center chloride? So edge center, 4 edge centers, 4 edge centers, and 2 body centers. 4 edge centers and 2 body centers. Not only phase center, even you can take the corner. Even you can take the corner, but here you need to take up what do we call 4 unit cells, many unit cells you have to take. See, for example, this is the particle we are talking about. This is the particle we are talking about. So here, this is at a by 2 distance. This is at a by 2 distance. Backside, there is one edge center along exactly, this is the edge I'm talking about. You can see here this one. So that is at a by 2 distance. Right side, I'm taking one unit cell. Here there is, if you extend the structure like this, here there is one Na plus ion. So here 1, 2, 3, 4. Below also there is one, what do we call, edge. Here also we have an Na plus ion top of it. How many? So here 1, 2, 3. Of course, all are edge centers. 3 edge centers of same unit cell. 1 edge center of right side unit cell. 1 edge center of above unit cell. 1 edge center of below unit cell. Each and every point you should know, then whatever it may be the question, you will be in a position to answer. The complete clarity you should know. So here, complete clarity you should have. Then only you will be in a position to solve the question. So here, that is at what distance? A by 2. So we can say coordination number, it may be phase center chloride or corner chloride. Its coordination number is 6. And here, the cation is present at what distance? A by 2 distance. That is okay. Then what about coordination number of Na plus? So coordination number of Na plus means the number of nearest Cl minus ions. The number of nearest Cl minus ions. But in case of number of nearest Cl minus ions, Na plus ions are present at body center. Na plus ions are also present at edge center. So first, if you see the Na plus ion which is present at body-centered Na plus ions, if you can see body-centered, see in this picture, you can see it clearly here. These are all green color things, corner particles, corner here, and here this is phase center. But this is the particle I'm talking about. So that is a body-centered particle, body-centered Na plus. Now you can see this body centered Na plus is surrounded by 6 face centers, of course, and 8 corners. But body center to face center, body center to face center, what is the distance? A by 2. Body center to corner, body center to corner, what is the distance? Half the value of body diagonal, that is root 3a by 2. Definitely this is a by 2. This is 1.73 to a by 2. So obviously this is the nearest neighbor. So for body centered Na plus, face centered chloride ions are the nearest neighbors. How many? 6. Where are the 6? 1. This is face center 2. This is face center 3. This is face center 4. This is backside face center 5. This is backside front side face center 6. At what distance? A by 2. A by 2. Then we also have Na plus ions at edge centers. We also have Na plus ions at edge centers. Edge centered Na plus is also surrounded by, so what do we call 6 Na plus ions. Now, for example, you can see this. So here, this is what do we call a corner particle, face center particle. 1, 2, 3. So this is what do we call this particle is edge center particle. This particle is a edge center particle. So here this is 1, this is 2, and this one is 3. Right side we have here, if you extend the structure, right side we have, that is 4. Above we have 1, 5, and here we have 1, 6. You can see here 1, 2, 3, and this is the 4th one. And the right side we have, and also here in what do we call above unit cell also we have. If you have to extend the structure, So here in that situation, here the coordination number, this is surrounded by what do we call 6 chloride ions. So this is corner chloride, face center chloride, and here we have what do we call this right side we have face centered chloride, and back side face center, and above also there is one face center chloride. How many? 6. So coordination number of Na plus is 6. Coordination number of Cl minus is also 6. Hence this type of packing is called 6:6 type of packing. But at what distance it is present from one unit cell, how many nearest neighbors are present, all those things can be asked. Anything can be asked. And the last one, that is packing fraction. So packing fraction, the definition is very simple. Packing fraction means the volume occupied by all particles by volume of unit cell into 100. Volume occupied by all particles, all ions, by volume of unit cell into 100. So we already discussed there are 4 cations and 4 anions. 4 cations and 4 anions. So radius of cation is 4 by 3 pi r c cube. So C means cation. Similarly, sorry, volume, not radius. Volume of anion is 4 by 3 pi r a cube, where A is anion. So here A stands for anion and C stands for cation. But how many such ions are present? 4 cations and 4 anions. So here this is 4 into 4 by 3 pi is common, and this is Rc cube plus Ra cube. So this is the total volume occupied by 4 cations and 4 anions. So volume of cations plus volume of anions. And this is basically a cubic unit cell. Hence volume of this cube, FCC or BCC, anything simple. So it is A cube, but I already told you FCC unit cell is formed by anions. Hence root 2A is equal to 4 times of radius of anion, and this A is edge length, this A stands for anion, and this A is equal to, bring this root to opposite side and substitute this A here, and here this will be 16 by 3 pi Rc cube by Ra cube into 2 root 2 by 64 R cube, and here this can be, here this is divided with Ra cube. So here Ra cube Ra cube by Ra cube, that is 1, plus Rc cube by Ra whole cube. But already told you for ideal calculations, radius ratio is taken as 0.414. Rc by Ra we have to substitute 0.414 cube, and finally if you simplify, you'll be getting that is 0.793. So that is 79.3 percentage. But if you can recollect only FCC unit cell, atomic unit cell, if you take, so that is 74 percentage packing efficiency. But here some voids are occupied, hence it has increased to 79.3 percentage. And this is about structure of rock salt, structure of NaCl. And this is the end of this video. Thank you very much.